Segmentation is the strategic process of defining and creating effective boundaries around contextual identities within networks composed of devices, users, and data. This involves both logical and physical construction to ensure that only necessary traffic is allowed to flow, mitigating risks associated with cyber threats like ransomware and malware. Over the past decade, segmentation has become vital in security frameworks due to these rising threats. Despite existing solutions like VLANs or firewalls, achieving comprehensive protection has been difficult, necessitating innovative approaches. This chapter explores modern segmentation models, challenges they encounter, and the advantages of redesigning segmentation strategies. The OSI model, a standard to describe networking communication processes, plays a crucial role in segmentation strategies, with 7 layers, including application, presentation, session, transport, network, data link, and physical layers. It defines device interactions. Understanding these layers, particularly Layer 2, data link, Layer 3, network, and Layer 4, transport, is essential for implementing network segmentation. These layers facilitate the enforcement of policies that prevent unauthorized access. This chapter explains these concepts briefly and how they're pivotal in aligning segmentation models, providing more comprehensive protection across organizational networks.
The OSI model serves as a foundational framework in understanding how data moves across a network. This model breaks down network communication into 7 distinct layers, each serving a specific function and interacting with the layers directly above and below to perform complex tasks that keep our digital world connected. Starting from the top, Layer 7, the application layer, is where communication begins and ends from a user perspective. It's the layer that applications operate on when initiating a network request or receiving data. This layer handles how applications interface with the network through protocols like HTTP, which structures the information into a format other layers can handle. As we move down to Layer 6, the presentation layer, the focus shifts to the translation of application formats into a common network format and vice versa. This ensures that data delivered from the network can be used meaningfully by the application, such as converting raw data into a structured language that applications can understand and display. Layer 5, the session layer, then sets up, coordinates, and terminates conversations across the network. It manages sessions between applications on different devices, ensuring that data exchange can be managed and is reliable. Next, Layer 4, the transport layer, manages the transfer of data sequences from a source to a destination, maintaining the quality and reliability of the channel. It regulates size, sequencing, and the reliability of messages between systems, often through error correction and flow control mechanisms. Layer 3, the network layer, is responsible for moving packets across the network, including routing them from the sender to the destination. This involves logical addressing so that data packets can find their way in a large or complex network. Below this, Layer 2, the data link layer, ensures that data is properly formatted for the physical network. It handles error detection from the physical layer, arranges data into frames, and manages the physical addressing of those frames for the subnetworks. Finally, at Layer 1, the physical layer, it's all about the transmission and reception of raw data streams over a physical medium. This includes everything from the cables and switches to the detailed specifications of transmission frequencies and signal encodings. Through these layers, the OSI model provides a robust structure to design and analyze network communication, offering a clear separation of responsibilities that helps simplify troubleshooting, development, and the implementation of new technologies. Each layer is crucial for the efficient and effective transmission of data, ensuring that digital communications are quick, reliable, and secure.
Upper layer segmentation focuses on specific OSI layers, notably the application, presentation, and session layers for preventing unauthorized inter-application communication. Application layer segmentation utilizes containers, like Docker, to isolate processes for security and functionality. Presentation layer segmentation involves separating application interactions to prevent data manipulation attacks, often seen in VoIP attacks. The session layer controls data exchange sequencing to validate communication order and authenticity. Sectors like defense and manufacturing often employ physical segmentation, using colored cables to segregate communication paths. This ensures robust safeguarding, particularly in environments demanding strict security measures.
In the realm of network design, the VLAN to subnet mapping offers a structured approach to managing how data travels across a network's various segments, particularly focusing on ensuring that data flows securely and efficiently between endpoints that may belong to different security zones or require distinct routing paths. This kind of mapping is critical in scenarios where networks are segmented into virtual local area networks, VLANs, and subnets for enhanced security, performance, and management. The diagram exemplifies the allocation of IP addresses in distinct blocks to corresponding VLANs across different campuses and branches. Each campus or branch has unique VLAN identifiers and subnet masks that dictate the IP range accessible within that segment. For example, at Campus A, VLAN 101 is assigned a subnet of 10.0.16.0/16, earmarked for corporate PCs, thus separating it from IoT systems on VLAN 104 with a subnet of 10.0.44.00/16. This separation is pivotal to ensure that devices in different VLANs communicate through controlled pathways, potentially mediated via routers or Layer 3 switches that can enforce policies about which VLANs are allowed to intercommunicate. Such mapping is not merely about managing logical addresses, but is part of a comprehensive segmentation strategy that includes Layer 3 or 4 access controls to regulate and monitor traffic across these segments. This vigilance helps in mitigating risks from internal and external threats, making it easier to enforce security policies and keep different sections of the network isolated as required. Moreover, this VLAN to subnet mapping plays a crucial role in organizational scalability and flexibility. By structuring the network into manageable and distinct blocks, organizations can expand or modify their network architectures more fluidly, while maintaining strict control over how data is sectioned and routed within the organization. This systematic organization is instrumental in reducing overall network complexity and enhancing the effectiveness of security measures.
Network-centric segmentation focuses on preventing unauthorized access by utilizing protocols and layered attributes. At Layer 4, IP, UDP, TCP, and ICMP are standard protocols used in conjunction with ACLs and security group tags to control access across the network. Examples include conventional TCP-based ACLs, which specify protocols and ports for traffic regulation, and more sophisticated role-based ACLs, using security tags assigned via systems like Cisco ISE. This chapter discusses how combining different OSI layers enhances segmentation efficacy, preventing lateral movements and unauthorized access across organizational networks while aligning with business needs. Directional segmentation helps in identifying how communication happens within networks, either north-south or east-west. North-south refers to communication between different zones or structures, commonly crossing through firewalls. The access device enforces segmentation through ACLs, ensuring only necessary interzone communication. East-west segmentation, crucial for preventing malware spread within a zone, focuses on controlling traffic where intermediaries aren't present, such as within a VLAN. Advanced strategies like security group tagging at Layer 2 address this challenge. Determining the right model, guided by organization architecture and risk, is foundational in effective network security planning. Selecting the appropriate segmentation model requires understanding organization architecture, network communication needs, and risk tolerance. Key considerations include evaluating the impact of not segmenting on business, existing policies that enforce segmentation, and the feasibility of maintaining continual operations during segmentation implementation. It's crucial to align segmentation with business objectives, such as protecting critical assets, securing government contracts, or enhancing brand reputation. Defining a segmentation charter helps establish goals while focusing on not disrupting vital business communications during integration. As companies progress in their security evolution, these evaluations become paramount in shaping effective segmentation strategies. Choosing the right architectural model for network segmentation fundamentally shapes its efficiency and protection efficacy. Layer 2 to access models limit routing to higher layers, using larger domains with minimal path selection. It could mandate re-architecting for devices, like older systems or specific environments unable to update regularly. Conversely, Layer 3 access models distribute VLANs across numerous switches and enable routing at lower layers, easing dynamic ACL application and enforcing control closer to endpoint devices. Understanding current architecture and its flexibility for redesign is crucial in seamlessly and effectively implementing segmentation, tailored to business and technical needs.
In today's discussion on network architecture, let's delve into the concept of switch-to-access design, which plays a crucial role in how data traffic is directed and controlled within a network. This architectural strategy is pivotal in handling how different segments of a network communicate, especially in enterprise environments where managing and securing data traffic is critical. At the core of this design are IP gateways, which are connected to the internet and serve as the primary route for incoming and outgoing internet traffic. Each gateway is connected via routed links to distribution switches. This setup ensures that each switch can handle data packets efficiently, directing them to the appropriate destination without unnecessary delays. A key element in this architecture is the use of switched virtual interfaces, SVI, at the level of each VLAN. SVIs represent an intelligent design choice, where each VLAN has its own virtual interface, which simplifies management and enhances security. The IP address for path selection resides on the distribution or core networking device, which leads to a streamlined routing process. This IP setup is essential as it dictates the communication path outside the local network and controls inter-VLAN traffic, ensuring that data flows are both secure and efficient. Downstream from these distribution switches, we find multiple access switches without allocated IP addresses. These access switches connect various network endpoints, such as computers and other devices, creating a large Layer 2 network domain. This layout emphasizes MAC address-based communication within the network, relying less on routing decisions at the access layer. Such a configuration helps in reducing the overhead on individual switches and focuses on segregating traffic right from the access layer, boosting both performance and security. By understanding and implementing switch-to-access design, organizations can achieve a robust, scalable, and secure network infrastructure. This design not only supports high-volume traffic efficiently, but also provides a solid foundation for implementing advanced security measures and network policies critical in modern digital enterprises.
Successful execution of segmentation revolves around strategic planning and effective policy implementation. Dynamic VLAN assignments allow endpoints to be grouped contextually, optimizing control without extensive manual reconfiguration. TrustSec, using security group tags, ensures granular segmentation within VLANs, preventing unauthorized intra-VLAN communications. Layered enforcement, employing ACLs, endpoint associates, and firewalls, distributes control, banning horizontal attacks, and maintaining network integrity. Such implementations require foundational knowledge of endpoints' behavior, deliberate planning, and a strict adherence to policy and management practices to maintain secure and efficient network traffic management in digital ecosystems.
In today's interconnected world, managing network segmentation is crucial for enhancing security and operational efficiency. The concept depicted here focuses on the Layer 3 to the access model, which is a sophisticated approach to network segmentation. This model allows for greater control and isolation by dividing the network into multiple VLANs, each with its own switched virtual interface, SVI, located at the access switch level. Unlike the Layer 2 to access model, where the SVI is often centralized at a higher network level, such as the distribution or core layers, having SVIs at the access level enables direct routing within the access switch. This minimizes the need for traffic to travel up to higher network layers for routing decisions, which reduces latency and the potential for bottlenecks. It also increases security by enforcing policies directly at the point of access, enabling immediate responses to security incidents within each segment. This structure is particularly advantageous because it supports fine-grained access control lists, ACLs, and can employ security policies tailored to the specific needs of each VLAN. By implementing direct routing at the access level, organizations can achieve a higher degree of segmentation and security, essential for protecting sensitive data and systems against lateral movement in case of cybersecurity breaches. As organizations continue to evolve and face increasingly sophisticated threats, the ability to quickly adapt and implement robust network segmentation using models like the Layer 3 to the access becomes more than just a technical necessity. It becomes a strategic imperative in safeguarding the integrity and availability of network resources.
Modern network challenges extend beyond physical environments, especially with the rise of cloud technology and virtual data centers. Virtual machines in hypervisors necessitate revised segmentation strategies, as they often lack physical trust segmentation capabilities. Utilizing agent software such as Cisco Secure Workload or Secure Endpoint offers robust policy enforcement by analyzing traffic patterns directly from the virtual environment. This ensures consistent, granular segmentation in and across both physical and virtual infrastructures. Furthermore, as cloud environments anchor more enterprise operations, intelligent overlays using IP tables and trusted tagging can maintain security policies across these dynamic setups, ensuring consistent safety across the technological spectrum.
Segmentation in network security is a crucial aspect for enhancing protection across an organization's network. It ensures that sensitive areas of the network are isolated and secured against unauthorized access and potential breaches. The segmentation strategy encompasses multiple layers, from the endpoint through to the application level. Starting at the endpoint, the focus is on securing devices by ensuring they can accurately present their identity. This includes applying identity verification processes to better understand the device's role and purpose within the network. By effectively identifying the devices, organizations can apply appropriate security policies tailored to the device's operational needs and risk levels. At the OSI Layer 2, granular segmentation using techniques like VLANs and access control lists, ACLs, helps minimize the scope through which potential security breaches could propagate across the network. By limiting communication paths and dynamically applying ACLs, traffic is restricted to only those segments of the network where it is necessary, thereby reducing the attack surface. Moving up to the application level, segmentation ensures that applications are secured by requiring user authentication before access is granted. This layer protects sensitive data and functionalities from being exploited by unauthorized users, thereby safeguarding the integrity and confidentiality of the application data. The diagram also emphasizes the importance of internal and external communications. By understanding and managing how data flows within the organization and how it interacts with external entities, the network can be safeguarded against vulnerabilities that might arise from both internal and external interactions. Validating and monitoring these communications ensure that they are necessary for business operations and are not posing security risks. Segmentation is not just about isolation, but also about how well the network can adapt and respond to threats through strategic enforcement of security policies at various network layers. This comprehensive approach not only shields individual network segments, but also provides an organizational-wide defense mechanism that adapts to varying security needs based on identity and access requirements.
Implementing effective segmentation strategies aligns with the zero trust paradigm, focusing on constant verification and minimal trust. Developing an endpoint segmentation plan outlines contextual identities, current roles, and traffic patterns for precise, dynamic policy application. Such planning ensures that business operations stay fluent while protecting essential data pathways from exploitation. Regular monitoring is integral. Traffic patterns change alongside business dynamics, necessitating adaptable metrics and updated enforcement policies. As organizations refine these methodologies gradually over time, they continue fortifying their security frameworks, making contextual segmentation a cornerstone of resilient, adaptive, and secure network architecture designs.
The endpoint segmentation plan is an integral part of a network security strategy, particularly within the framework of zero trust security architecture, where trust is never assumed, regardless of the network location. This plan illustrates a structured approach to segmenting network access and permissions based on the types of devices and their business alignments. In this context, different sections of the network are assigned specific security protocols for authentication, AuthEHC, and authorization, AuthZ. For instance, the corporate segment utilizes .x for authentication and VLAN DACL for authorization, ensuring a robust security posture for sensitive corporate resources such as user devices, servers, and applications. For segments that accommodate guests, simpler authentication like MAC address bypass, AAB, and web redirect are employed, coupled with similar authorization strategies as used in the corporate sector. This helps in managing the access of less trusted devices while still providing necessary functionality. The plan also extends to specialized segments like Internet of Things, IoT, and Industrial IoT, IIoT, where device-specific considerations such as liquid flow and temperature sensors require targeted security measures, again using .x or MAB for authentication with DACLs for network access control. Furthermore, the Building Management Systems segment covers devices linked to facility operations such as HVAC and elevators, using simpler authentication mechanisms reflecting their operational necessity but lower data risk. The security section notes how crucial systems like cameras and door systems are secured, considering their role in overall physical and network security. This segmentation allows for tailored security policies that reduce the risk of lateral movement within the network, thereby enhancing the overall security framework by enforcing policies as granularly as necessary. By implementing such a segmentation plan, organizations can significantly mitigate risks and improve the security and efficiency of network traffic management.